Here we go. All right, today's speaker is Asger Törnquist here at the Toronto Set Theory Seminar. And his title is The Mathematics of a Model of the Mind in Psychology. Go ahead, Asger.
Thank you very much, David, and thank you for inviting me to speak. This is obviously an unusual topic for me to be talking about psychology. And I will try to introduce this model of the mind that a psychologist called Jens Mammen, who's a Danish psychologist, has introduced. I'll try to explain the background, but the thing that caught my attention in this is that it's actually formulated in terms of an axiomatic system in mathematics, this model of the mind. So let me try to give you an overview of Jens Mammen's theory. So Jens Mammen is a Danish psychologist, and he's retired now. He just turned 80, so he's a professor emeritus at this stage. But he has throughout his career worked on an idea he had for a model of the mind, or a model really for the interface between the inner world of the human mind and the outer world, which we perceive or interact with or reflect upon. And as I alluded to, this is quite an interesting theory for a mathematician, because Jens Mammen, he formulated his theory in terms of sort of an axiomatic system, sort of like we know in mathematics. So he has his system, or his theory is based on that you need to have a set U of objects in the world, and he calls this the universe. And then he wants a topology S on U, and I'll explain on the next slide or two what that S is being used for. But it may be useful to already now say, if you're sort of familiar with Kant's notion of categories, this is sort of Kantian categories, that the elements of the topology are Kantian categories of objects. And then there's a collection C of subsets of U. These are the choice categories used for distinguishing certain special objects in the universe. And then S and C must play together nicely and satisfy certain axioms. And I will tell you about the axioms in a few slides. But I also want to say, which Jens Mammen said to me from the beginning, he never intended to explain how the brain does what he says it does. He just wanted to describe what he as a psychologist observes that the brain does. So he's not trying to explain how his model is being realized physically by the brain. He is not a neurologist, he's a psychologist. And so he said very early on, this is an extrinsic or extensional model of the mind. How the mind or brain does what he claims it does, he doesn't know how it does that. So some features and some motivations of this theory. So as I already alluded to, theoretical psychologists and philosophers have proposed many models of the mind over the years. And oftentimes this idea of broad categories that the mind uses to organize data that it perceives is the basis of many of these models of the mind. So for instance, to make this a little bit more concrete, if a mind, such as my own, has experienced a sense something, such as stones on a beach or something like that, then my mind would form a broad category of stones, and it would recognize when an object is a stone, belongs to this general category. And see, what Jens Mammen and other psychologists that he works with or worked with feel that this misses is that very clearly human beings form special attachments to individuals or animals or special objects in the world. So if I went down to the beach and I found a particularly beautiful stone on the beach, there are millions of stone on the beach, but oh, I found that one. I picked it up and I singled it out. I chose that stone. I liked it so much, and I brought it home to my house. And everyone who knows me knows that I'm pretty clumsy, so I probably would drop that on the floor sooner or later. And then I would pick it up, and somehow I would know that it is my distinguished stone. And so the mind does this all the time. It singles out certain objects. And why is that important for psychology? Maybe it's not so important for psychology that the mind singles out stones and things like that. But what is really important if you're looking at human interaction is, of course, interaction with other people. So the mind singles out special other people. So, of course, something about my father or mother had to be in a talk about psychology. So it'll be my father. So my father belongs to the general category of fathers that my mind has formed. But the point here is that my father is of special importance to me, and somehow my brain has singled him out into a special category of a distinguished person, distinguished from other fathers, and he's special to me. He's not just a father, he's not just in the category of fathers in general, but he is my father. He is singled out by my mind. So our mind seems to do this. It singles out individuals and objects that are animals that are special to us. So now a very common remark that I've heard people make when I'm trying to describe this model of the mind is that, well, couldn't we just solve this by saying, well, the mind can single out an individual or an object by simply singling out that, you know, my father is at the intersection of all the categories in my mind that he belongs to. And that might be, this is sort of the Kantian answer as far as I know. And this might be a very good way of trying to get around this, but it doesn't really reflect what the psychologists observe. It seems as though the human mind has some sort of special function or capacity for singling out individuals or individual objects. So, so from the working psychologist point of view, it would be interesting to have a model of the mind that reflects what they see in the clinical setting, clinical practice. And this is what Jens Mammen set out to do. He wanted to have two kinds of categories, broad categories that he called sense categories. And he also wanted to have some special categories that he called choice categories or distinguished categories. And now we get to the axiomatics, finally. It's the mathematical formulation, home turf. So a Mammen space, and this is my term. I came up with this because I got tired of not having a short name for it. So a Mammen space consists of a non-empty set U equipped with a Hausdorff topology S. So S is for sense because it's modeling the sense categories. These are the broad categories. And it has to be a perfect topology. And what that means is that every non-empty open set has to be infinite or set in a more convoluted way. No non-empty open set is finite. So a family C, we also need this family of categories in the universe, a family of subsets of the universe, which would be the things that we're singling out, the special categories of special people, special objects. So, and this category, so he called it choice categories, the inventor of this. So I used script C. So there is a non-empty choice category. So there is a non-empty set C in script C. And for every non-empty C in C, every non-empty C in C contains a singleton. So the choice categories are supposed to help you zoom in on individual objects that you find are special somehow. And so we should be able to completely zoom in on something within a choice category, so a singleton. And then we require that C is closed under finite unions and finite intersections. And furthermore, S and C have to play together nicely. And the first thing is that the only choice category, which is also a sense category, is the empty set. So the sense categories are not for zooming in. These are the broad categories the category of all stones, or the categories of all fathers. Bear with me here, because of course it's sort of idealized. I said that it's clear from what it says up here with the perfect Hausdorff topology that the universe is infinite, and every broad category is infinite. So I suppose if I'm talking about the category of fathers, I'm somehow imagining there are infinitely many fathers, but so that's a little bit idealized.
So I have a weird question. So
yeah, go on.
So if it's true that these choice functions, they reflect that we have special attachments.
Yes.
This means that everyone really likes the empty set, or I mean.
Yeah, I think essentially the only reason it is a little bit weird that the empty set would be a choice category, because you're choosing nothing. But what I think it reflects is actually that I think it reflects that that Jens Mammon quickly realized that it's practical if C was an ideal. Now, he didn't really want to require it's an ideal, but I think in many situations, many actual realizations of this this axiom system, it'll be an ideal. So I think that may be why that the empty set became a choice category. It's a little bit funny, I admit that.
I see. Thanks.
Now, and finally, to the final requirement of playing nicely together is that if you have a choice category C in script C, and you have a sense category S in script S, then C intersected with S is again a choice category. So if I use a choice category to zoom in on some objects, and then I intersect with a broad category, well, then I've just zoomed in even further. So that's why it should still be a choice category. So I'm already used to terminology.
I need an example to understand this. So that means if your chosen stone that you have at home and that you really like, if it's blue, then sort of to your choice categories also belong the category of all blue things and of all stones, or?
No, it's intersection. I'm zooming in further. Fewer objects.
Oh, so I see. So it could be that all the choice categories are singletons from that. I mean, nothing so far has.
Yeah, and it has to be closed on a finite union. So you could maybe take all finite. So that would be a good candidate for the choice categories would be the collection of all finite subsets of the universe.
Yeah, that helps. Thanks.
Excellent. Then, so if C prime is the ideal generated by C, it's quite easy to show that the triple USC prime is again a Mammon space when USC is. So actually that if you could, from my point of view, I've sort of generally just assumed that the choice categories form an ideal, because this doesn't seem to be much gained by assuming it's not. So anyhow, so that's just sort of a practical thing for a mathematician anyhow. So now we come to the sort of central definition that started a lot of mathematics in this project, and the reason that Jens Mammon came to me in the first place. So, so given a Mammon space, so a triple USC, what Jens Mammon wondered was actually if he can use S and C to describe all categories that can be formed in the universe. So a category is simply a subset of the universe U, right? So he was wondering if actually you could describe all subsets of U using just the two kinds of categories, namely the sense categories and the choice categories. And not only that, he'd actually like that you could finitely describe any subset of U using just elements of script S and script C. So he singled in on the following funny definition, which is the notion of a complete Mammon space. So a Mammon space USC is called complete if every subset of the universe can be written as the union of S and C, where S is some sense category and C is some choice category. So basically, in a very simple way, he wants every subset of the universe to be described by the sense categories and the choice categories. In a very simple way, I say, because he simply wants them to be, wants every subset of the universe to be a union of a sense category and a choice category. And he singled in on this because he would actually he would sort of really like to have an ideal model somehow of the mind, a model of the mind which has succeeded in describing every category in the universe using these two kinds of categories that the mind can form, namely the sense categories, the broad categories, and the choice categories. And just as a quick remark, in case you have a complete Mammon space, then actually C automatically, the choice categories automatically form an ideal. Because if you took something which is a choice category and you took a subset of that, then that subset also would have to be, so call that subset X. It would also have to be written, you would have to be able to write it on this form. But no sense category can be a subset of a choice category unless it's empty by the axioms. So actually, if you can write everything as the union of a sense category and a choice category, then every subset of a choice category is again a choice category. And therefore, since the choice category is also closed in finite unions, they will form an ideal. So this is what he singled out as sort of the ideal model of his axiom system, and he called it complete. And now things got really interesting mathematically, already a long time ago, because he asked the questions: do complete models exist? Do complete Mammon spaces really exist? And in the early 1990s, Hofmann-Johnson, who was a professor at the University of Aarhus and professor of mathematics and statistics, he explored these questions together with Jens Mammon, and using the axiom of choice, he was able to answer this question here. So here's the answer, using choice. There are complete Mammon spaces. So it is possible to have a Mammon space which is complete in that simple sense that every subset of the space is the union of a sense category and a choice category. So in a very simple way, if you believe that's a model of the mind, that model of the mind is can describe every subset of the universe, so every category, simply using the two kinds of categories, the sense categories and the choice categories. But it was actually much more specific what Hofmann-Johnson proved, because he showed the following, that if T is any perfect Hausdorff topology on an infinite set U, then there is a finer perfect Hausdorff topology S, such that as finer perfect Hausdorff topology, so finer than T, such that U as C is a complete Mammon space. And what is C? C is actually just the closed discrete subsets of U with the topology, with respect to the topology S. So actually, not only can you get a complete Mammon space, but you can sort of fairly concretely describe what the choice category should be, and this finer perfect topology, well, it just refines your favorite perfect topology. And actually it refines it maximally, and that's the key observation. So what is it? So the key idea was these maximal perfect topologies that, as far as I know, the first paper that I could find that mentions these maximal perfect topologies is from 1943, a paper by Hewitt. So here's the definition. A perfect topology T on some set U is called a maximal perfect topology if no topology which is strictly finer than T is still perfect. And it's a routine application of Soren's lemma to see that, well, so Soren's lemma, basically the axiom of choice, any perfect topology is contained in a maximal perfect topology. So you can always refine a perfect topology to become a maximal perfect topology. And then here comes the lemma to remember. And the lemma to remember is the lemma to remember because you have to remember it for the next slide. So here we go. So let T be a perfect topology on U, then the following are equivalent. T is a maximal perfect topology on U. That's equivalent to saying that for any X, which is a subset of U, if it is the case that for all open sets V in our topology T, we have that that the intersection of X, our set X, and V is always either empty, so has cardinality 0, or is infinite. Then X is actually already in T. So this is just gives you a very hands-on criteria for maximality. It just says that every time you have X, which is a subset of U, and it is a candidate for being added to the topology, because every time you have an open set V in your topology and you intersect X with V, then you either get the empty set or you get an infinite set. So it's a candidate. And then maximality is just formulated by saying that if it's a candidate, if X is a candidate to be an open set in the topology, it already is in the topology. So that's all that this lemma to remember is saying. And the thing that you need to remember, perhaps most importantly from the lemma to remember, is the moreover part. That if A and B holds, then every discrete subset A or B, so they're equivalent. So if A holds or B holds, then every discrete set is closed. So now, so this is the lemma to remember. So remember the lemma to remember, and especially remember this last part, the moreover part. So here's the way that Hofmann-Johnson he solved Mammen's problem about the question if there exist these complete Mammon spaces. So Hofmann-Johnson's theorem about the existence of complete Mammon spaces follows from the following lemma. So if, it's probably needed to say, if S is a maximal perfect Hausdorff topology on a set U, oh, sorry, no, it's good because there's an if and only if. I had to read further, sorry. S is a maximal perfect Hausdorff topology on a set U if and only if every subset of the universe U can be written as X, every set X subset of U can be written as S union C, where S is in the topology and C is closed and discrete in the topology S. And I'm actually going to prove this for you. So proof of the, or at least one direction of this. So given a subset X of U, we do the almost obvious thing. We define C to be the set of those X in our set X, which can be isolated. So that is to say there is a V in the topology. So the V intersected with X becomes just singleton lowercase x. So it's just the set of those lowercase x and x, which can be isolated by isolated using an open set, some open set V. Well, then C is discrete. And therefore, by the lemma to remember, so remember when we have a maximal perfect Hausdorff topology, any discrete set is closed. It is a closed discrete set. Now, for every V in S, if you look at V intersected with X, take away C. So if you remove C from X, well, every time I intersect, take some open set V, and I intersect what is left of X after I remove C with some open set. Either I get the empty set, so I didn't hit this what was left at all, or I must get something infinite, because otherwise, if I got something finite, I could just, you know, use the Hausdorffness to single out a single point in X, take away C, so with X without C, and I could single out a single point there using an open set, but then that would have to be in C already. Does that make sense?
Yeah, that makes sense.
Excellent.
At least to me, it does.
Oh, you're not the only one. There's some thumbs ups coming. So good. So, well, but then by lemma B, so part B of the lemma to remember. If it's always the case that every time you take an open set and intersect it with your set, in this case, X without C, you get either the empty set or you get an infinite set. Well, actually, then that set already has to be in the topology because it's a maximal perfect topology. But now, of course, X is just the union of C and X without C. That bit is clear. So now I've written X as the union of something in S and something which is in which is closed and discrete, and therefore I've proven the lemma. So that was the lemma. So this is Hofmann-Johnson's this is his key observation. And so now, of course, he gets, we get a corollary. So not only do we have a Mammon space, so why does the lemma now give us a complete Mammon space? Well, it just tells us you take a maximal perfect topology, that's your S, that's the sense categories, and you take the collection of all closed discrete sets with respect to that topology, that is your choice category. And there you have it, because everything can be written on this form. You have a complete Mammon space. So nice topological solution to Mammon's question. And actually, the corollary makes it perhaps even better, because there is a complete Mammon space with a countable universe U. That's pretty clear, because I could take my countable universe to be the rationals, and I could let S be the maximal perfect topology on Q, which is finer, not the, but a maximal perfect topology in Q, which is finer than the topology generated by open rational intervals. And there is such a thing, and now you have a maximal perfect topology on the rationals, and you apply Hofmann-Johnson's lemma, and you have a complete Mammon space with a countable universe, namely the rationals. So far so good, because now we're getting somewhere. But we did use the axiom of choice because we use Zorn's lemma. So we know that by now that using the axiom of choice, we can get a complete Mammon space, even with a countable universe. And I feel pretty relaxed about the axiom of choice, and I think most set theorists do. So I'm not particularly startled by this, but this was all intended to be a model of the mind in psychology. And so I think Jens Mammon felt a little bit shocked that you needed to use a non-constructive principle in order to achieve a complete Mammon space. So he asked, well, Jens Mammon, the inventor of all of this, he asked if you really needed the axiom of choice, but Hofmann-Johnson was pretty optimistic that you did. So he conjectured that the existence of a complete Mammon space implies the axiom of choice. This is a bold conjecture, in my opinion, but I've been taught by Simon Thomas many years ago that when you state a conjecture, you should state the most bold version that is not, that you cannot prove false. So maybe it's sort of a conjecture in this way. Now, here's the main result that we have. And that is in Cohen's first model, which is a model of set theory in which all the axioms of set F are true, but the axiom of choice is false. Any perfect topology can be extended to a maximal perfect topology. And it follows that the existence of a complete Mammon space does not imply the axiom of choice, because in the first Cohen model, you have a maximal perfect topology on, say, the rationals or something like that. And that gives you a complete Mammon space. But of course, in Cohen's first model, the axiom of choice is false. So that shoots down the conjecture. And how does the proof work? The proof works by mimicking Halpin and Levy's proof that in the first Cohen model, every filter can be extended to an ultrafilter. And this is the ultrafilter lemma. But I promised in the abstract that I had open questions. And there are many open questions in the paper that we've written. And I'll give the reference to the paper later. but there are many open questions, but here are some of them. So actually, so this is a little bit of a workaround to disprove this conjecture by going into the first Cohen model and going through an adaptation of Halpin and Levy's proof. It would be much, much nicer if you could do the following, that you could simply take the ultrafilter lemma and use the ultrafilter lemma to prove that there exists a maximal perfect topology on some infinite set. And then you'd be done in a possibly much slicker way. But I wasn't able to do that, and that's why I had to work very hard and dust off the proof of Halpin and Levy's theorem. Another question, and this was my original idea for disproving the conjecture, was actually to try to use the first order compactness theorem, which is of course equivalent to the ultrafilter lemma, assuming AC plus small amount of choice. My original idea was actually to prove that there is a complete Mammon model by using the compactness theorem. But I failed miserably at doing this. And the reason I failed miserably at it is that you need to say that you're working with a perfect topology. And that entails saying that some things are infinite. And saying things are infinite is really difficult in a first order language. So I didn't succeed at that. So that's an open question. Sort of really, it's one open question, looks like two, but it's really one open question. Can you use, say, the ultrafilter lemma or the first order compactness theorem to prove that there is a complete Mammon model? I'll repeat this question later, along with many other questions. So the other result, of course, was, do you really need any choice at all then? And so here's an attempt at saying, yeah, you probably do, though it's not a great answer, but it is a answer. So work in the theory ZF plus all subsets of the reals are Lebesgue measurable, or if you prefer, all subsets of the reals are Baire measurable. Then there are no complete Mammon spaces with a countable universe. So then you can't have a complete Mammon space with, say, universe, the natural numbers. And as you all know, in Solovey's model, all subsets of the reals are Lebesgue measurable. So therefore, theorem B gives us the following nice counterpoint to theorem A, that there is a model of set theory without the axiom of choice in which there are no complete Mammon spaces with universe N. And I should have added on this slide a question I don't know the answer to, and that is, I don't know if it's possible to, could it possibly be that there is a complete Mammon space with the underlying set being much larger in Solovey's model? Is there a complete Mammon space with an uncountable universe? I don't know the answer to that. So this is what I know, and it's not ideal, but it does tell you that it seems like we do need some sort of non-constructive principle in order to achieve a complete Mammon space, certainly for a countable universe. So I'll very quickly say something about the idea behind theorem B. I won't go too much into the details, just to give you sort of an idea of what goes into that. I won't say so much about theorem A because it's a little bit long. So the idea behind the proof of theorem B is pretty simple. We'll combine the following proposition and lemma. So now remember, there was a lemma to remember, but now there's also a proposition to remember, and it's the following proposition. So it says that let USC be a Mammon space, and suppose there is a subset X of the universe such that for any V and for any open set V which is non-empty, the sets V intersect X and V intersect V without X are infinite, then USC is not complete. So if you have a subset of the universe which somehow dodges the open sets, they dodges them infinitely, really, because, well, and doesn't just dodge them, it hits every open set, a non-empty open set infinitely, but it also hits its complement infinitely. So it's sort of sitting there in a way that's getting away from the open sets. So that then USC is not complete. And then there's a measure theoretic lemma. Of course, there had to be, because it's a theorem about measure or bare measurability, if you like. So suppose that n, so this is not really about Mammon spaces, it's just a general measure theoretic lemma about perfect Hausdorff spaces. So suppose that n comma s is a perfect Hausdorff space, so S is a perfect Hausdorff topology on the natural numbers. If for every n in the natural numbers, the following set, the set of those, so I've called this script A sub n, script subset, it's the set of those subsets of n, so that for all open sets V in our topology S, if n is in V, then V intersected with A is infinite. If these sets here, for every n, the script AN are the back measurable, where of course we identify the power set of the natural numbers with the Cantor set, and therefore you can put the Lebesgue measure in the Cantor set. You do the coin flipping measure, where it's going up through the Cantor tree, you always flip a coin, an equal coin, I assume, and you get a measure like that. So that's what I mean by the back measurable. Then the set of those X, which is, or the set of those subsets of n, X subset of n, so that for every non-empty open set, it's the case that V intersect X and V without X are infinite. This set has full measure. And similarly for bare, measurable, and co-meager. And the point, of course, is that if I know that all, so what I'm saying here is that if all of these sets script AN are Lebesgue measurable, what I actually get is a set of measure 1 of X, which show that you can use the proposition to remember to show that so the point here is that I actually get a huge set, right? I get a set of full measure of X that are candidates to showing that if actually this S here was the topology of a complete Mammon space, well, it couldn't be, because this X will, an X in this set here will show by the proposition to remember that it's not complete. That was a very terrible way of saying that, but did it make any sense?
You could have just proved this set is non-empty to show that this Mammon space is incomplete. But you're showing it has full measure even.
Yeah, so I'm showing in a very, very strong way that it is non-empty. Thank you, David. That's an excellent way of saying it. We need to show that this set is non-empty, because if I can show that it's non-empty, then I can take this X, and I can use the proposition to remember to see that USC is not complete. But actually, I don't just show that there is such an X. I'm not just showing this set here is non-empty. I'm actually showing it's enormous. It has full measure. Or if you prefer to work with bare measurability, and instead, what I'm saying is it's co-meager. So there's an enormous number of candidates to solving, to come up with this X. So I'll give you the proof of the proposition to remember, because I'd like to use that. It's a proposition to remember because we'll need it again in a moment. So I'll repeat the proposition so that USC be a Mammon space, and suppose there is an X, which is a subset of our universe, such that for every non-empty open set, V intersect X and V without X are infinite sets, and then USC is not complete. So the proof is quite simple, but as I said, we'll use this proposition again. So assume, aiming for contradiction, that USC were complete. And then my X here could be written as S union C for some S in script S and C in script C. That's just the rules of the game. Now, by star, we can't have that S is non-empty, since, well, S is, of course, in script S. And if X is written as S union C, then S would be a subset of X. And now if S, of course, is an open set. So if it's non-empty, it should intersect the complement of X infinitely, which is impossible if it's a subset of X. So S can't be non-empty. So S must be empty. But of course, if S is empty, that just says that X is equal to C. So I just get X is equal to C. And C, of course, is in script C. So now I have that X is in script C. And now, of course, if you look at the condition up here, it's totally symmetrical between X and the complement of X. So actually, the exact same argument will show you that the complement of X is also in script C. It's also a choice category. And now I've written U as the union of X and the complement of X. And of course, script C is closed under finite unions. So that is because X and the complement of X are in C. This is in C. And now I have that U, the universe, is in script C. But one of the axioms of Maman spaces says that the only choice category, which is also a sense category, is the empty set. So I really have a problem now. So yeah, so that's the proof of the proposition to remember. So it's just a small combinatorial observation, really, but we'll use it again, at least twice. And then there's the measure theoretic lemma, and I'll sketch the proof of that as well, but let me just repeat it. So suppose that the natural numbers with S, script S is a perfect Hausdorff space. If for every n in the natural numbers, the set of set script an that you have here is Lebesgue measurable, then the set script A, consisting of candidates to show that S is not the topology of a complete Mammon space, has full measure. So I've already defined my A script an up here, and I'll just define row of an to be those subsets of A where the complement of A is in an. Now, I want you to observe that the set script an is invariant under finite changes. And why is that the case? Well, look at this setup here, script an. If I have some A which is in script an and I change it finitely, that will not change the conclusion here. That intersection, if that intersection is infinite and I change A finitely, that intersection is still infinite. So script an is invariant under finite changes. And that's actually then true of row of an as well, if you think about it. And now it follows, since script an and actually also row an, that they're Lebesgue measurable, it follows that they must either measure 0 or 1. So once you have a subset of the power set of natural numbers, which is invariant under finite changes, and it's Lebesgue measurable, it's a well-known fact that then it has to have measure 1 or 0. Now, using the fact that S is perfect, as I'm not going to do this step, but you can actually show that the power set of the natural numbers is the union of script an and row of script an. And therefore, we must have that the measure of an and the measure row of an is 1. Because so let me say something about that, right? So if this set measures 0, then it's easy to check that then this would also measure 0. So, but they can't both have measure 0, because then the whole space would be the union of two measure 0 sets. So therefore, one of them would have to be not 0. But once one of them is not 0, well, then by this invariance under finite changes, actually it must have measure 1. And since actually row an and an must have the same measure, they must both have measure 1. So I'm skipping a little step here, but this is the essential idea that you end up with, that script an and row of script an actually both have measure 1. And therefore, of course, now, well, I can take the intersection of all of the ans and intersect that with all of the row of ans, and I'll have still have a set of measure 1. And I'll continue the proof in the next slide. So what are we doing? We're still trying to prove that this set A here has measure 1. And what have we achieved so far? We have achieved that the measure of this big intersection of all the script ANs and all the row ANs is 1. And now I claim that actually the intersection of all the script ANs and the row of script ANs is actually a subset of script A. And this is probably the last thing I'll prove in this talk, so bear with me. So to see this, let X be an element of the intersection of all the script ANs and all the all the row of script ANs. And we'll argue as follows. If V is non-empty, then there must be, V is a non-empty open set, then there must be an element N in V. And so by definition of script AN, since X is in script AN, right? So X is actually in the intersection of all the script AN, so it's certainly in script AN. Well, by definition of that, as soon as N is in V and X is in script AN, then actually V intersect X and V intersect X complement must be infinite. And what I've just shown you is that for any V, which is open and non-empty, the sets V intersect X and V without X are infinite. And the proposition to remember says exactly now that then NSC is not complete. And that finishes the proof. And actually, it was funny. Yeah, so now I mixed it all up. So to finish this, the proof, not just of the lemma and the proposition, but also of the theorem, theorem B that we wanted to prove. So I mixed up this. This is supposed to say, and now this is how we prove theorem B. And this here, the second to last line, that should be, and that finishes the proof of the lemma. So sorry about that. I'll try to work on my slides a little bit better and keep the various components separate in the future. Now, so that's the proof of the lemma. And now comes the last bit of the talk. And I wanted to include this because there's a number of open questions here and very few results. So the last few slides will be about cardinal invariants associated to this. So what we'll consider is the cardinality of a basis of S. So especially in the case where S is the family of sense categories in a complete Mammon space. In other words, we'll be considering what is called the weight of the topology S, where S is the topology of sense categories in a complete Mammon space. And I'm going to work only with the universe N from now on, so countable universe. And then I'll define two cardinal invariants. The first is U sub T, and this is the infimum of all the weights of topologies T, which are maximal perfect topologies on the natural numbers. And then I'll also define UM, and that's the infimum of the weights. So the weight of S is the size of the minimum size of basis for S. So this is the infimum of all the weights of S, so that there exists a C, which is collection of subsets of natural number. Oh, and here it should be, so sorry, it should say C. I'll correct this on the final version of the slide and I send it on to David and whoever wants to see it. So it was supposed to say here that it's the infimum of the WS where there is a C such that NSC is a complete Mammon space. Does that make sense? It should say NSC is a complete Mammon space.
It's just the smallest weight of a topology that is part of
can be the topology of a complete Mammon space.
Accountable, yes. I guess.
On a countable set. Yes, exactly. And now we've seen that every time we have a maximal perfect topology, then we also get an associated Mammon space. But it's not clear, and it's not even true that every complete Mammon space arise in this way. You can cook up examples that show that that's not how they all arise. It's just one way of getting such spaces. Now UM must therefore be less than or equal to UT, because every time I have a maximal perfect topology, I get an associated Mammon space. But there may be many, many kinds of weird Mammon spaces that have nothing to do with maximal perfect topologies. Of course, both of these are less than 2 to the olive 0 because we're dealing with the cardinalities of subsets of the natural collections of subsets of the natural numbers. So we're dealing with subsets of the power set of the natural numbers is the best way of saying that. And actually, and I find this slightly remarkable, that Mammon, who is a psychologist and who started, well, it has to be said, he started mathematics, started undergraduate mathematics in Copenhagen sometime in the early 60s and dropped out after a year and then became a psychologist and a psychology professor and so forth. But I'm very impressed that already in the 1980s, he proved this theorem for himself, that so the least cardinality of a basis for a topology, which is the topology of a complete Mammon space, is greater than olive 0. So I've got to say, that's pretty good going for a psychologist who took 1 year of university mathematics. But we can actually do better. So, and Mammon himself wondered, could you do better? So he wondered what values this could have. And he noticed, of course, that if you have the continuum hypothesis, you get that is olive 1, because has to be less than the continuum, and he just proved that it's uncountable. And there are several open problems about the size of and UT, but we do have a few results. So let me just say what those results are. So has to be bigger, greater than or equal to the additivity of the bare ideal. So, so of the meager ideal, I should say. And in particular, because under Martin's axiom, the additivity of the meager ideal is 2 to the olive 0. So if you take, under Martin's axiom, if you take the union of fewer than continuum many meager sets, you will get a meager set. That's a well-known theorem. So the additivity is 2 to the olive 0. So under Martin's axiom, you actually get that is equal to UT, which is the continuum. But that's not the end of the story, because in the Baumgartner-Lever model, is equal to UT is equal to olive 1, which is less than 2 to the olive 0, which is olive 2 in that model. And what is that Baumgartner-Lever model? And why do I say the Baumgartner-Lever model? Well, it refers to a model of set of C obtained by starting with a ground model where CH holds, and then adding olive 2 Sachs reals iteratively. So that's what I mean by the Baumgartner-Lever model. And it's, of course, saying the Baumgartner-Lever model is misleading, because I could start with many different models of where this ground models where CH holds. But you know what I mean. You add olive 2 Sachs reals iteratively. Oh, and I actually included the proof of that. I had forgotten. The proof, well, it's quite easy. So, and we still have a little bit of time, so I'll go through that. So aiming for contradiction, I'll suppose that NSC is a complete Mammon space with a basis B for S, which has size less than the additivity of the meager ideal. And then I'll look at B prime, those would be the V. So those are the open sets, which are, well, all open sets, of course, that are non-empty will have to be infinite. And since they're subsets of the natural numbers in this case, they'll have to be, they would have to be countable. But actually, I want to look only at the collection of open sets which are non-empty, and their complement is also infinite. And it's easy enough to find an open set which is not everything, because I'm working in a Hausdorff space. So B prime is non-empty. And for each V in B prime, I'll let MV be the set of those X which are subsets of N, so that X intersect V is equal, the cardinality of X intersect V is equal to the cardinality of V without X, which is infinite. So I look at all the subsets of the natural number that intersects my given V infinitely, and which also intersects the complement of V infinitely. So, oh, sorry, that was completely wrong. So it intersects V, the X that intersect V infinitely, and if you remove X from V, it's still infinite. That's what I want to say. And actually, it's kind of important. So I say easily MV is co-meager. And it's not terribly hard to check this. So it is really easy. But it's actually an important point to make, that if I take an infinite set V, whose complement is also infinite, and I look at the set of those X that intersect this V infinitely, and where that also intersects the complement of V infinitely, that will be co-meager. But try to do this with measure. I'm going to get back to this when I state one of the unsolved problems. Try to do this with measure. Then this is the step that's going to go wrong. So MV is co-meager, but try to do this with measure and you'll get into trouble. Anyhow, to finish the proof, now argue as follows. Well, since B prime is a subset of B, so it has cardinality less than B, it has cardinality less than the additivity of the meager ideal, and therefore, if I intersect all the MVs, that will still be co-meager. Intersected MVs where V is running over B prime, so that'll still be co-meager. So I'll take X, which is in the intersection of all the MVs, and then X contains no non-empty open set W, and if you remove X from the natural numbers, it can't contain a non-empty open set. Because if it did that, it would contain a basic open set, and then it would even contain, using a Hausdorff property, it would even contain an open set whose complement is also infinite. So it can't be the case that X contains a non-empty open set, and the complement of X cannot contain an open set. And therefore, by the proposition to remember, it follows that NSC is not complete, because now I've come up with this X. In fact, in this co-meager set, I found a co-meager set of X that will show that NSC is not complete. Does that make sense? David says yes. Luciano says yes. Oh, good. Some of you are saying yes. So that was the proof of this. And as I said, there's an open question here on one of the last slides. And now the result, finally, something about the result in the Baumgartner-Lever model. So in the Baumgartner-Lever model, this model where you start with a ground model which has the continuum hypothesis. And then you iteratively add Aleph to Sachs reals. And what you get is, we show that you get a model where UM should probably set UT here, because UM equal to UM is not terribly impressive. So UM is equal to UT, which is equal to Aleph 1, which is less than 2 to the Aleph 0, because it's Aleph 2 in this model. And of course, if you're familiar with the Baumgartner-Lever model, what you will know is the so-called ultrafilter number in the Baumgartner-Lever model is Aleph 1, even though the continuum is Aleph 2. And this is one of the famous applications that they have of their model in that paper by Baumgartner-Lever, which is a very famous paper because it's one of the early papers about iterated forcing. So the proof is based on the following two lemmas, which I will not prove, don't worry. So let T be a perfect topology on a set U. Suppose that for every X in U, the filter T star X, which is simply the set of those W without singleton X, so that W is an open set and X is in, that should have said W. So I'm looking at, I'm looking at, what am I doing? I'm taking an X in U, I'm taking a point in my space. I'm looking at all the open sets. So where it is now highlighted with blue, it was supposed to say W. So what I do is I look at all the open sets that has X as an element. And now, of course, if I look at all the W without singleton X, that's going to be a filter. Because if I take two open sets that both have W, so have X as an element, and I intersect them, then oh, sorry, it's not a filter, it's just a collection. Oh, I should have said it generates an ultra. So it generates a filter. It's closed under intersections, but it's not necessarily closed under, sorry, it should have said the filter generated by this is an ultra filter. I'll work harder on my slides. So the point is this: if every time you have this sort of, this is really the neighborhood basis of a point, and then you remove the point from the space where you're looking at this neighborhood basis of the point, you remove that from the space, what you're left with is something that generates a filter. And if that filter generates is always an ultra filter, then T is actually a maximal perfect topology. So that's one ingredient. And the other ingredient is that the continuum hypothesis implies that there is a perfect topology T on the natural numbers, so that for every n in the natural numbers, T star of n, that's sort of funny, it's almost the neighborhood basis. And it's not quite a filter, it should say the filter generated by T star n. It generates a selective ultra filter. And if you're familiar with the Baumgartner-Lever model, the point that can be used to prove that the ultra filter number in the Baumgartner-Lever model is Aleph 1 is exactly that. If you take a selective ultra filter, so a Ramsey ultra filter in the ground model, and you look at what that generates out in the forcing extension in the Baumgartner-Lever model, then a selective ultra filter will still generate a selective ultra filter out in the Baumgartner-Lever model. But of course, that ultra filter from the ground model, it will only have, it has a basis of size Aleph 1, and it's and the iteration doesn't change Aleph 1. So anyhow, sorry, this is getting very messy. I meant to explain what we were doing. If you're familiar with the Baumgartner-Lever model, I think there's a chance this made sense.
I think this makes total sense. I don't
Oh,
think
good. All right. So this was the plan. So the plan is not to be terribly original in proving this. It is actually to look at what Baumgartner and Lever did and try to then arrange a situation where you can essentially apply one of their main results. So finally, the open questions. So first open questions about UM and UT. Can UM and UT be separated? And that is it consistent with set of C that UM is strictly less than UT? So that's my first question. I have no idea if they're always equal or if they can be separated. The result about the Baumgartner and Lever model does hint very strongly that there's a connection between UM and the ultra filter number. So here's my next question. If U denotes the smallest cardinality of a basis for an ultra filter on the natural number, so that is the ultra filter number, what is the connection between U, the ultra filter number, UM, and UT? Can they be separated, or are they always equal to each other? And I have no idea. And finally, recall that we have seen that UT is greater than or equal to UM, which is greater than or equal to the additivity of the meager ideal. And I said to you, there's something in the proof. I defined the set MV, which is co-meager, and that was central in the proof. But it's not clear at all that that set MV has measure 1. So therefore, the proof of this cannot easily be adapted to show this, quite surprisingly. And that is a problem I don't have an answer to. Can you prove in set of C that UT is greater than or equal to UM, which is greater than or equal to the additivity of the Lebesgue? So this is the Lebesgue null ideal. And I have no idea. And the proof for the Baire property does not immediately work. And I don't even know if I believe that this can be proved in set of C. So again, I pose it to you. Solve this problem for me. And finally, a recap of open questions I already mentioned. a version of what I already said that is perhaps even stronger. Does the existence of a non-printable ultrafilter imply that there exists a complete Mammon space? Does the ultrafilter lemma, so all filters can be extended to an ultrafilter, implies the existence of a complete Mammon space? Or equivalently, does the first order compactness theorem imply the existence of a complete Mammon space? I have no idea. Does the existence of a complete Mammon space imply that there is a maximal perfect topology? I have no idea. I'm going to guess no, but I really have no idea. So these are some of the questions. In the paper, there are even more questions. And so I'll give you the reference now to the paper. Now, first of all, Jens Mammon has written a book called A New Logical Foundation for Psychology. And if you want to know the psychological background in detail and much, much more about how he came up with his axiom system and what are the reasons for choosing these axioms, you should look at that book. It has all the details for that. If you want to find the reference to Hofmann-Johnson's results that the axiom of choice implies that there is a complete Mammon space, then it's an unpublished preprint. It can be found online at this address here. I'll send around the slides to those who want it. And of course, finally, there is the paper by Jens Mammon and me, a set theory and a model of the mind in psychology. And I'm going to put out a warning right now. The archive version is full of errors. And we have been revising it. And a new version of the paper is going to go on the archive in the next few days. And that will sort out a lot of frustrating typos and small errors and weird things that we should have caught before we put it on the archive. But at the end of the day, well, I'm very thankful to the referees who pointed out our many bizarre typos and many weird places where we wrote something that we obviously did not mean to write. So a better version is coming on the archive, and eventually a published version, which will be even better, will appear somewhere. And that is all I have to say. So thank you for your attention.
Oh, thank you for your talk. Very interesting. Are there any questions from the audience? Do you have time for questions? I realize that you're in a hurry, right, Asger? Give us time for a few.
I have to run out of here in 10 minutes. Yeah.
Oh, good. Okay. So quick, give us some questions.
Hi, Asger. This is Alan Dow.
Hi, Alan.
Great talk. Thanks. You should look up a paper by Eric Van Douwen.
Yeah.
Called Maximal Topologies, I think it's called, in the 80s sometime. So he looked at these maximal topologies, and his interest was, could it make it a regular topology and not just simply Hausdorff? And he introduced a notion called no-dec, nowhere dense sets are closed. And he proved that these, and I'm not sure if he needed regular for this, but these maximal no-dec topologies are extremely disconnected. So your result about ultrafilters was a consequence in his paper that every filter base was an ultrafilter.
Nice.
And also another more recent result in the 2000s, there are the the dynamics on omega star, and there are these what do you call them, idempotents, and there's a special kind of idempotent. I think it's mentioned in Heinemann and Strauss's book, and the orbit of one of these maximal idempotents is exactly one of these spaces. So it's one ultrafilter on N, and you just take its orbit under the integer addition in N, and you end up with one of these spaces. So that might be relevant to your,
this is fantastic, because these are the things that I've been wondering about, that I could sort of only connect, I could only connect ultrafilters to maximal perfect topologies in sort of one direction. And I was wondering if it could be done in the other direction, and I could make it work. So this is fantastic news. This actually, this is helping me a lot.
Now, as I said, I don't know whether his result, Van Douwen's, required regular. So his big deal result was he could make the maximal Hausdorff, he could make it regular. That was his interest. But and in that sense, in that setting, he proved they were ultrafilters. So I don't.
That's very, very interesting. Okay, that gives me that I see. I've been looking for a result in the opposite direction. So even if it requires regularity, that is a big improvement for me, that there is any connection in that direction at all.
That would answer the Lebesgue measure question too, doesn't it? Because then it's like adding a random real, isn't it? That you wouldn't preserve ultrafilters.
I guess it might. It might help in that question. I'd have to think.
Because I think your result with the bare measurability is just adding a Cohen real destroys ultrafilter. Yeah.
Yes. I get it. Yeah, I get it. Yeah, I think you're right. I think you're right. Oh, fantastic. I'll have to look into that.
Wow, okay, so that was a really interesting question. I was going to ask much more simply, how can it be that no one has thought about the relationship between UT and U? But maybe people have. And
yeah, so maybe that will actually also be a way of connecting these things. So yeah, so it's certainly not the case that we haven't thought about this. On the contrary, it's something that I thought about, but had no result.
Sure, no, but I mean, UT is not something that might have been defined by you.
No, it would be very natural to think that this would have been defined somewhere else. Yeah, I'm not claiming any originality in defining that, but I didn't see it defined in any of the references that I found. So, but it's a very, very natural cardinal invariant to look at.
Asger.
Yes.
This is Valery Mishkin.
Yes, hello.
I just wonder, didn't you think on homeomorphism groups of these moment spaces?
No, I have not. I haven't thought about this because I suppose the questions that I focused on were the ones that Jens Mammen had asked me or had asked in his various writing. So that I haven't looked at the homeomorphism.
I have a feeling that there is some relationship to ergodicity. So yeah, some ergodic transformation. So, but there's just a feeling.
Yes. Yeah, of course. I mean, it's sort of in the sense, I suppose, that they are sort of extremal spaces in that.
Yeah, it should be related to ergodic theory somehow.
Yeah. Anyhow, yeah, but again, this is an excellent question, that there is and especially also if you look at the homeomorphisms of this. So one of the things you can also wonder about, of course, is that there are many, many ways in which you can take a perfect topology and then extend it to a maximal perfect topology. And generally speaking, the expectation I would have is that most of the time you'll get non-homeomorphic spaces. I mean, these extensions that we have because of Soren's lemma, they should all be very different. But I have not looked at that. It's just a feeling that I have.
Okay, thank you.
Actually, I have a paper with Van Mil where we produced two non-homeomorphic. That was hard to do, to get two of them that were not homeomorphic.
Now that you mention it, I actually think I did run into your paper at some point. Yeah, now that you mention it. Yeah, I should look at that again. Yes.
Any more questions?
I'm just typing away because I'm taking down some notes from your questions, just so I don't forget what I should check out.
So we can expect we can expect the updated version of the archives?
Yeah, there'll definitely be an updated version of the archive. I'll submit that over the weekend. I actually meant to have done it yesterday, but it was probably good that I didn't rush it, because then I found more things to correct today. So
Okay, good. Yeah, it's interesting anyway. Just yeah.
I agree. It's really interesting. So I guess we'll thank you again.
Yeah, I can't find the clap button, so I'll just have to thank you.
oh, well, I want to thank all of you for listening and for your insightful comments. And then now that I'm speaking, so I realize people are probably sitting in various different places around the world, not necessarily in Toronto, but now that we are, now that I'm speaking at the set theory seminar in Toronto, I just wanted to say I'm really, really looking forward to coming to Toronto to the Fields Institute next year for a while. It'll be an absolute thrill to be back in Toronto for a few months, and hopefully for the whole of the program. So anyhow, thank you all very much for listening and for your wonderful comments. And I promise there will be an updated version of on the archive posted over the weekend, which means that it's probably available Monday or Tuesday. I can't remember their update schedule, to be honest.
Okay.
Thank you.
Thank you.
All right. So this concludes the session. Goodbye,
You're
everyone.
welcome to Toronto.
Looking forward to it.
Okay. Bye now.
Bye.
Bye.